Assalamualaikum. We are from RCDCS 1434D. We'll presenting about system of linear equation SLE problem by using linear algebra method. Method that we can use which are Gaussian elimination method, Gauss-Jordan elimination method, Cramer rule, and inverse method. First of all, we need to construct a linear equation 5 by 5. This is example of linear equation. We have 5 linear equation. Equation 1, equation 2, equation 3, and equation 4, and equation 5. From this equation, we need to construct a matrix 5 by 1 for each column in matrix 5 by 5. After that, we can construct a 5 by 1 for column V. This is an example what we construct a matrix 5 by 1. Furthermore, we must construct a matrix of 5 by 5. A is example what we construct a matrix of 5 by 5. Lastly, we need to augment matrix A with B. Now we can move to the first method. M is the augment matrix A with V.
Okay, so from this matrix, we can use Gaussian elimination method. Okay, from the matrix, the first step is we have to add 1 over 2 times row 1 to row 2, and the output will be like that. And then we have to subtract 1 over 2 times row 1 from row 3, and the output will be like in the slide. And then we have to subtract 3 over 2 times row 1 from row 4. And then we have to subtract 1 over 2 times row 1 from row 5. After that, we have to add 1 over 3 times row 2 to row 3. And the output will be like this. And then we have to subtract 1 over 9 times row 2 from row 4, and the output will be like in the slide. And then we have to add 5 over 9 times row 2 to row 5. And we have to subtract 5 over 3 times row 3 from row 4. After that, we have to subtract 2 over 3 times row 3 with row 5. And last step, we can add 8 over 13 times row 4 with row 5. And after we have complete all the steps, we can extract the equations from the matrix so that we can find our x5. And then after we extract the equation, the value of the x5 will be like in the slide. After we find the value of x5, we can solve the other equations by find the other value of x, such as x4, x3, x2, and x1. So, after we already find the value for each x, the value after we substitute for each x, and the answer will be x1 will be equal to 2, x2 will be equal to 4, and x3 will be equal to 4, x4 will be equal to 3, and lastly, x5 will be equal to 4. And That is the last for Gaussian elimination method. So now we move to Gauss-Jordan elimination method.
Now we are using Gauss-Jordan elimination method. We begin our system of 5 linear equations represented here as an argument matrix. Our primary goal with Gauss-Jordan elimination is to form this matrix into what's called reduced row echelon form. This means we aim to achieve an identity matrix on the left side, which will then directly give us the value for our variable x1, x2, x3, x4, and x5 on the right side. The first step in Gauss-Jordan is to create a leading one in the top left corner of our matrix. We achieve this by multiplying our first row by 1 over 2. Once we have the leading one, we use it as a pivot to eliminate or zero out the element directly below it in the first column. We do this by adding row 1 to row 2 and subtracting row 1 from row 3. Continuing with our first column, we apply similar elimination steps to make the remaining element below the leading one equal to 0. Here, we subtract 3 times row 1 from row 4 and then subtract 1 times row 1 from row 5. Now that our first column is complete with a leading one and all other zeros, our attention shifts to the second column. Our next goal is to establish a leading one in the second column position. We will accomplish this by multiplying row 2 by 2 over 9. With our new leading one in the second column, we now use it as a pivot to eliminate the element both above and below it in that column. On the left, we subtract 1 over 2 times row 2 from row 1 to 0 out of the element above our pivot. Then we proceed the 0 out of the element below the pivot. We add 3 over 2 times row 2 to row 3 and subtract 1 over 2 times row 2 from row 4. We have one more element to 0 out in the second column, so we add 5 over 2 times row 2 to row 5. Now our focus shifts to the third column. Following the pattern, we aim to create a leading one in the third column position. This is done by multiplying row 3 by 3 over 10. Immediately, we use the new pivot to clear the element above it in the third column. We add 13 over 9 times row 3 to row 1. Continuing to clear our third column, we now work on the remaining element using our leading one. We add 1 over 9 times row 3 to row 2 to make the element in the second row. Third column becomes 0. Then, we proceed to eliminate the element below the pivot. We subtract 15 over 9 times row 3 from row 4 and subsequently subtract 20 over 9 times row 3 from row 5. Moving systematically, our attention is now on the fourth column. We first establish our leading one in the fourth column position by multiplying row 4 by -3 over 30. With this new pivot, we begin to zero out the element above it in the fourth column. We subtract 23 over 30 times row 4 from row 1 and then subtract 11 over 30 times row 4 from row 2. We continue to clear the fourth column by eliminating the element below our pivot. We subtract 3 over 10 times row 4 from row 3 and then subtract 8 over 3 times row 4 from row 5. Now we are at the final column. Our last leading one needs to be in the fifth column. We create this by multiplying row 5 by -30 over 31. We are in the final steps of achieving our reduced row echelon form. With our last leading one in the fifth row, 5 column, we used to eliminate all remaining non-zero elements directly above it. We subtract 137 over 130 times row 5 from row 1. Then we add 41 over 130 times row 5 to row 2. And finally, for this column, we add 69 over 130 times row 5 to row 3. To complete the process, we perform one last elimination. We subtract 10 over 30 times row 5 from row 4. And there we have it. Our matrix is now in its reduced row echelon form. The left side is a perfectly identity matrix, which means we can directly extract the solution for our variable from the right hand column. Based on this final matrix, we can find that S1 equal to 2, S2 equal to 4, S3 equals to 4, S4 equals to 3, and S5 equal to 4. This illustrates the elegance of Gauss-Jordan elimination method in solving system of linear equation.
Okay, now by using the Cramer's rule method, we can solve matrix A. Firstly, we need to construct matrix A1 by substitute column V into first column in matrix A. After that, we need to construct matrix A2 by substitute column V into second column in matrix A. Then, we need to construct matrix A3 by substitute column V into third column in matrix A. Furthermore, we need to construct matrix A4 by substitute column V into fourth column in matrix A. Lastly, we need to construct matrix A5 by substitute column V into fifth column in matrix A. After constructing all the matrix A1 to A5, we can find determinant of x1, x2, x3, x4, and x5 by dividing with determinant A, which are solved for x1. We need to divide determinant A1 with determinant A. After that, for x2, we need to divide determinant A2 with determinant A. Next, for x3, we need to divide determinant A3 with determinant A. Furthermore, for x4, we need to divide determinant A4 with determinant A. Lastly, for x5, we need to divide determinant A5 with determinant.
Inverse method. To find the solution for the given system of linear equations, we can use the inverse method. To do the inverse method, we need to find the inverse of the matrix. First, we can augment the matrix with its identity. Then, solve the matrix by changing the left side into the matrix identity. After we finish, we need to multiply the matrix with V to get the answer for each x. Discussion. In a non-homogeneous system, we can classify the system into two classes. The first one is consistent, which has a solution, while the other one is inconsistent, which doesn't have any solution. Consistent can also be classified into two classes, unique solution and many solutions. The condition for inconsistence is when A equals 0, but B is not equal to 0, which is impossible when we think about it. Then, for unique solution, the condition is when A is not equal to 0 and B is any real number. The last one has many solutions. The condition is when both A and B are equal to 0. Let's take a look at the example question. Consider the non-homogeneous system. Find the values of A such that the system of linear equations will be inconsistent, has a unique solution, and has an infinitely many solutions. For question A, we need to change the matrix into a row echelon matrix. leaving the last row to answer the question. Now we have two equations inside the matrix. The first is a squared minus 4 and a minus 2. Inconsistent. The condition for inconsistent is when a equals to 0, but b is not equal to 0. Substitute a and b with the previous equation, and then solve the equation. The answer we got for the first equation is a equals to negative 2 and a also equals to 2. And for the second equation, a is not equal to 2. Therefore, the final answer is equal to negative 2. Now, I'll hand it to Lutfi for the next question.
For question B, to find the unique solution, we can just do like this based on the syllabus that we have studied, which is A is not equal to 0 and B is element to real number. So the answer will be that is A not equal to negative 2 and A not equal to 2. For the C question, to find the many solution, we can just do like this based on the syllabus that we have studied, which is A is equal to 0 and B is equal to 0. So the answer will be A will be negative 2 and will be 2 and A equal to 2. So the answer for the final answer is A equal to 2.